Hello everyone, welcome to this new video on analytic functions. This is going to be the first video in the series. We will be seeing what is meant by analyticity in this video, what are going to be the necessary conditions for any function to be analytic, and how you can use the conditions for analyticity to check whether the given problem is going to be analytic or not. So these will be the topics which will be covered in this first video, which is the basic video on analytic function. Come, let's move into the video. First, we will define what is meant by complex variable. We have normally seen or worked with real functions. Say suppose we have functions like f of x is equal to x square. What is the role of x? X is going to be a real number, in which case this function will be called as an real function. Now we have been introduced to a extension of this real number called as a complex number. So what is a complex number? Any number of the format z is equal to x plus iy is called as a complex variable, where x and y are going to be two independent real variables, and the I over here is called as the imaginary part, which satisfies the criteria I square equal to minus 1. In this expression of z is equal to x plus iy, the first term which is present over here will be referred as the real part of the complex number. And the second quantity which is present over here, y, is called as the imaginary part of the complex number. So, when I have a combination of a real part plus I times of my imaginary part, then this quantity is referred as a complex variable. Now, what is a complex function? If I have z is equal to x plus iy and w to be equal to u plus iv as two complex variables, such that corresponding to each value of z, there exist one or more values of w, then w is called as a function of z and is written as w equal to f of z. Like how we have defined a function using the real variable, this real number can be replaced by a complex number or a complex variable, and I can define a function of a similar type. So say suppose I have f of z to be equal to defined as z square. So now this kind of function where I use complex variable to define a function will be referred as a complex function. This the f of z will now be represented by the variable called as w. So I say w is equal to your f of z. Hence, what happens over here? We see that w, which is going to be u plus iv, w, which is being defined as u plus iv, can now be expressed as f of z, which is nothing but f of x plus iy. Now, let us take an example and see how this works. Let us consider the same example as f of z is equal to z square. So what is this f of z? This is going to be z square. So I will be having f of x plus iy the whole square. So what will be my z square? F will not be there. X plus iy the whole square. What is this x plus iy the whole square? So let me use a plus b the whole square formula. So it becomes a square plus b square plus 2ab. So this is my a square plus b square plus 2ab. So now this gives me x square. This is y square. And what we know about the imaginary part I square? I square is always equal to minus 1. So it becomes minus 1 times of y square plus, this is the only term that contains I. So let me pull my I in the front, and you have it as 2xy. Hence, we see that w, which was u plus iv, has now been expressed as x square minus y square plus I times 2xy. Now, this is a complex number and the right hand side is also a complex number. Whenever two complex numbers are equated, it means that the real parts are equal and the imaginary parts are equal separately. So what I can write out of this? I can write u, which is a function of x comma y, is nothing but x square minus y square, and v, again a function of x comma y, is nothing but, what is v, along with I, whatever is present, that is going to be my imaginary part. Okay, ignore the I, don't take it along with I. So you will have this v of x comma y as 2xy. So my u, the real function, is going to be x square minus y square, and the imaginary part of the function is nothing but 2xy. So this is how we can express a complex variable as a function. Now we will move on to the next concept called as analyticity. What is meant by an analytic function? A single valued function f of z is said to be analytic at the point z0 if it possesses a derivative at z0 and at every point in some neighborhood of z0. So the main keywords over here is, when do you call it to be analytic? If it possesses, what it has to possess? A derivative. Where it has to possess the derivative? It has to possess the derivative at every point in some neighborhood of z0. So if this happens, then what do you call this function as? You call it as an analytic function. So keep in mind, derivative has to exist in and around some neighborhood. What do you mean by this neighborhood? So if I am going to consider a point z0 and then take a small radius, very small radius, and then consider a circle around it, then this points which lie inside this circle will be called as the neighborhood of z0. So, if my function f of z is going to be analytic at this particular portion and also in this neighborhood portion, then you call it to be analytic, or so we call that if it is going to have a derivative at z0 and all the points in this periphery, then if the derivative exists, then you call this f of z to be an analytic function. So the main concept is possessing a derivative. So when the function is differentiable, derivative. So what do you mean by derivative? The function is differentiable, and most probably what has to be taken care of? It must be a single valued function. What do you mean by single valued function? When you give an input to z, the output must be only one in nature. Now, if I have f of z to be defined as z square and I give z as the value to be equal to 2, say. So, what will be the outcome for it? It will be 2 square. What will be f of 2? 2 square, which will be equal to 4. So, this is single valued. But if I define my function f of z to be equal to square root of z and I give the input as 4, then what do you think will be the output? It will be plus or minus 2. So in which case, do we call this as a single valid? No, we don't call this as a single valued function. Okay, so a single valued function, if it is going to be having a derivative at this particular point and also in the neighborhood of the point, the derivative exists means, then you call the function to be an analytic function. The other names for analytic functions are regular function and holomorphic function. So what do we know or call if this is not going to happen? What is the converse of it? That is, if the derivative is not going to exist, does not possess a derivative. So the derivative is not existing at that particular point. Then that particular point is called as a singular point or a singularity of f of z. So what do you call this as? You call it as a singular point or singularity. What is a singular point? You don't have a derivative at that point. So you call this as a singular point. So can we have some example for singular points? We will have this example. Check if f of z is equal to z by z square minus 1. What are going to be the singular points of this function f of z? So what is going to be singular point? A point at which derivative does not exist. So f dash of z must move towards infinity. So this is going to be does not exist. Does not exist means existence is not valid. So it has to move towards infinity. So I will have to find my f dash of z. What is my f dash of z? Go differentiate your function. Z square minus 1 the whole square. Z square minus 1 you keep as such. Z on differentiation is 1 minus z you keep it as such. Z square minus 1 on differentiation is 2z minus 1. So now my f dash has to move towards infinity. So f dash has to move towards infinity means then I will have z square minus 1 minus 2z square plus 1 divided by z square minus 1. The whole square has to move towards infinity. What is this infinity? How I can write this as? It is nothing but 1 divided by 0. In which case, the denominator over here has to move towards what quantity? It has to move towards 0. So, I have z square minus 1, the whole square to move towards 0. So, this implies z square minus 1 moves towards 0, which implies z square moves towards 1. And so z is equal to plus or minus 1 is going to be my singular points. So how do you get your singular points? Just differentiate your function and equate the denominator to 0. The denominator equated to 0 gives you your singular point. I hope you are now comfortable how to estimate the singular point of any given function. Thank you.